Welcome to everyone. My name is Noussaiba Mennai. I am a PhD student at the University of Khenchela, Algeria. On behalf of my co-authors, I would like to present our conference paper entitled Identification of PV Module Parameters through an Iterative Method. This is the presentation outline that we are going to cover. Starting with the introduction. The growing need for sustainable and eco-friendly energy has driven the rapid expansion of photovoltaic systems. And to optimize the performance and integration of PV systems into the power grid, accurate modeling, simulation, and testing are essential before going to practical applications. Several studies have explored different approaches to PV module modeling by using equivalent circuit models, such as the single-diode model SDM and the double-diode model DDM. And since the SDM provides a good compromise between simplicity and precision, it was a popular choice for PV system simulation. In this context, PV module manufacturers typically provide us with some key parameters like the short circuit current, the open circuit voltage, and the maximum power, etc. under different conditions like the standard test condition STC and normal operating cell temperature and OCT. However, parameters like series resistance and parallel resistance RS and RP, which significantly influence the module's electrical behavior, are often not given by the manufacturer. So the main contribution of this work is to present and validate an iterative method for accurately determining these two unknown parameters by applying this method to two different types of PV panels, the monocrystalline shell solar and the second one polycrystalline from Kyocera manufacturer. The extracted parameters were then used to build the PV model in the Matlab Simulink environment. Then simulation results were obtained under both STC and NOCT conditions. Finally, the accuracy of the model parameters was evaluated by comparing them against experimental data and with results from previous studies. Starting with the modeling of the PV panel. In this paper, the SDM model is used to characterize the behavior of the PV cell and so the PV module. This is the equivalent circuit of it. And this is all the mathematical equations used to describe the whole model of the PV module. Moving on to the calculation of the two unknowns RS and RP of the PV panels. So the idea is based on the fact that there is a unique pair RS and RP, ensuring that the maximum power calculated by the IV model in the previous equation 1, denoted Pmax model, matches the maximum experimental power from the datasheet, denoted by Pmax experimental. So an iterative approach is used here to iteratively determine the value of RS and consequently the value of RP, and of course this process will be in repeat until Pmax model will be equal Pmax experimental as described by the equation number 6. So in this work, the Newton-Raphson NRM method is used to do this work, and this method is defined by the following equation number 10, where xn is the present value and xn plus 1 is the successive value, which is regarded as an approximate root of the equation fx equal to 0 if the condition in here in equation number 11 is fulfilled. Here epsilon is the tolerance. It is for us to choose this tolerance. So this is the flow chart describing this the whole algorithm used to determine RS and RP by the mean, of course, of an NRM method. And the following equations are also used for this purpose. Here RP mean it is used as an initial guess for the value of RP, the parallel resistance. And for the initial guess of RS, it is taken 0. We start from 0. In our case here, the algorithm should stop if this criterion, or called also convergence criterion, is fulfilled. Here it is the absolute value between the difference of Pmax model and Pmax experimental, this absolute value or the error. Moving on to the results and the discussion. To validate this algorithm, the PV module model is initially implemented, as we said earlier, in Matlab Simulink environment by using the previous mentioned mathematical equations. Then two different types of PV panel here are used. The first one is with a power rating of 140 watt. It is monocrystalline PV panel. And the second one from Kyocera manufacturer, it is with a power rating of 200 watts. And it is polycrystalline with a polycrystalline technology. The algorithm is then programmed and executed within the Matlab environment to determine the parameters, the unknown parameters RS and RP during STC and on OCT. This is the two models of the two panels. This is for the Kyocera and the other one for the Shell Solar. So after plotting the first results, IV and PV curves for both PV panels under the two under STC and NOCT conditions, and comparing these plots in three critical or remarkable points from the datasheet, we can see that the characteristic curves derived after this simulation of both PV panels accurately match at the three critical points outlined in the table 1 given by the manufacturer. And here we're talking about the short circuit current, maximum power, experimental power, and the open circuit voltage. Also, by taking a look at the computed or calculated parameters for both PV panels, especially here RS, RP, and I0, which are typically not included in the manufacturer datasheet, we can see that that they were successfully determined using the Newton-Raphson based algorithm under both NOCT and standard test condition. This conclusion is supported by the relatively small differences observed between the data provided in Table 1 and then Table 2. Moving on to the evaluation of the precision of this considered method. So to do so, we have taken an experimental data for the KC200GT PV panel at STC, and we have plotted this experimental data against the data found in this work and in two other previous studies. The results, as you can see in figure number 7, demonstrates the closest match to experimental data of the output voltage and current compared to other two methods. Also, by using the experimental data, we have then evaluated the accuracy of this method by calculating the root mean square error and the average relative error for n experimental values of output current by using equation 13 and 14. We can see clearly that the Newton-Raphson iterative method achieved the lowest RMSE value of 0.24 ampere compared to the other methods. Similarly, for the average relative error, we can see that the considered method in this work has the lowest ARE among the other methods. Here it has a 2.38% compared to 5 and 3% for the other two methods. Finally, these findings suggest that the calculated RS and RP values by the mean of the NRM-based algorithm enabled the development of an accurate model of a PV module, and this indicates its effectiveness. Conclusion. In this research, we have seen the modeling and parameter estimation of PV modules using the Newton-Raphson based algorithm, and the algorithm was validated by applying it to two different PV panels from two different market segments. Also, the different results obtained from the algorithm's implementation showed its effectiveness in accurately determining the PV module parameters. Particularly here we are talking about the RS and RP values. The accuracy of the presented method was then evaluated by comparing the RMSE and ARE values of the output current with other two techniques, and the results revealed that the Newton-Raphson based algorithm achieved the lowest root mean square error and average relative error among the others, indicating its remarkable precision. Finally, these findings suggest that this algorithm could be used for PV module parameter estimation and modeling, and future work could focus on refining this algorithm, specifically in determining the ideality factor. This is the references used in this presentation. Thank you so much for your attention.